About this a little bit more. So this shows a pretty standard schematic overview of the history of the universe. So you have time running from left to right, right? So what this picture actually shows that, we know that from observations of the cosmic microwave background, we know that a few 100,000 years after the Big Bang, the universe, protons and electrons recombined, which made the universe transparent to electromagnetic radiation, right? And this is why we see these nice temperature fluctuations in the cosmic microwave background, which tell us all about the initial density fluctuations in the universe. So we know from these observations that the universe was neutral, right? But if we look at the environment, or if we look now at the universe in between galaxies, we see it's highly ionized, right? So we know that at some point in the past, a major phase transformation must have occurred, right? And we call this the epoch of reionization, and I talked a little bit about this already. And schematically, it is illustrated here with the emergence of the first ionized bubbles that formed around the first galaxies. And the clustering properties of these first galaxies caused these bubbles to grow to sizes that are much larger than you could possibly power with individual galaxies, right? Because galaxies were strongly clustered, especially the first ones. Their collective ionizing power really drove the growth of these early H2 regions, right? So these bubbles grew and grew until eventually the amount of space that still contained diffuse neutral hydrogen was basically gone. And when that happened, we basically say that reionization was complete. There's still a lot of neutral hydrogen gas left, but only in the most densest gas. Right, and a slightly different focus, I'll focus on a slightly different version of that now. I'll focus on especially the thermal and ionization state of the universe as a whole. Right? So now we can identify, so now time is running from top to bottom. So we know that at recombination, hydrogen becomes neutral. Right? The universe cools adiabatically from then on. And hydrogen cools, I mentioned this earlier. So hydrogen cools especially fast as the universe expands further and further. And the reason is that, well, adiabatic cooling of baryons, which is a non-relativistic gas, is faster than that of the CMB, right? So the baryons cool much faster, like 1 plus Z squared, yes? While the CMB basically cools as 1 plus Z, right? Or if you want to think of it in terms of a scale factor, it cools as a to the minus 1 or a to the minus 2. Right? Now, following cooling, at some point, structure starts forming and hydrogen gets heated. This is the very first thing that happens. Right? This is at the very early stages of reionization, when the first bubbles, before even the first bubbles start growing, we know that there are ionizing photons, high energy ionizing photons, that are able to penetrate the neutral gas much further than the ionization regions. And we know that these high energy photons likely were very efficient at heating the gas in the universe. Right? And also the non-ionizing photons with energies a bit below the hydrogen ionization threshold, in principle, they could enter into the neutral IgM. And in principle, they could be, when they were absorbed, when they were redshifted into one of these Lyman series resonances, they could radiatively cascade and produce a Lyman-alpha photon, right? And that Lyman-alpha photon would bounce around, scatter around many times. And these many scattering events would also contribute to heating of the gas, right? And we'll talk a little bit about that more about that later on. So the very first thing that happens with structure formation is basically that we have heat injection into the universe. Now this is then followed by hydrogen ionization or reionization, right? And once, then reionization is complete and we're in the post-overlap era, and as we saw from Matthew's diagram, things are very easy once you're a post-overlap universe, right? Things become significantly more simple. That's at least what I got out of it. Okay, and just to show you a plot of the universally average temperature of the gas in the universe as a function of redshift. Right? At redshift of 1,000, when the universe recombines, the gas temperature and the CMB temperature remain closely coupled for a while. And that is because recombination is not complete. there's a little bit of electrons left, and scattering of CMB photons off these free electrons cause the temperature of the gas and the CMB to be very closely locked together. Now, as the universe expands, the densities goes down, and collisions between individual particles become rarer. Collisions become less efficient, become rare, more rare, not rarer, well, rarer is fine too, I guess. They become more rare. And we see that the adiabatic cooling, actually, I guess this is the main point. The adiabatic cooling, at some point, the density, these residual electrons cannot really couple the gas temperature to the CMB temperature anymore. That's because of these reduced densities and the inefficient collisions. And the gas starts cooling adiabatically then. And as I was mentioning earlier, this cooling is faster than that of the CMB. Right? That was this adiabatic cooling that went as 1 plus z squared. Now, at some point, this cooling has to stop. It cannot go on indefinitely. We know that during this period, redshift 20, 30, 50, structures are forming. Gravitational potential wells are getting deeper. Baryons are assembling in it. And at some point, there will be dark matter halos that have gas that is dense enough that stars can form. And there are some estimates in the literature that are actually quite interesting that, I think the first star in standard CDM was estimated to have formed at about a redshift of 65 plus or minus 2, right? At 2 sigma, like 95% confidence levels, right? So this would be the most rarest density fluctuations within our observable universe, right? And if you then, just as the standard baryonic processes suggest that this very first star would have formed at redshift 65, which is interesting. I think there was another paper that was written then if you have non-Gaussian fluctuations, right? That you can actually, you could in principle form stars even earlier, as early as redshift of 130 or 100, depending on, of course, on the slope of the matter power spectrum. But it was sort of argued that if you have first stars forming at redshift of 130 or something like that, this might have led to the formation of planets at redshift of 100 or so, so. It was actually quite interesting because it sort of suggests that life may have originated as early as redshift 100 in the universe under non-Gaussian conditions, which is pretty cool. In any case, we know that in standard cosmology, the first structures form at a redshift of around 50, 60, right? But the impact of the heating doesn't kick in until a bit later, right? Now, once you start dumping, especially X-rays emitted by accreting black holes into the universe, this temperature, it takes very little energy to let the temperature of the gas go above the CMB temperature fast. Right. And this is actually something that, we would like to test all of this. We'd like to see if this is actually happening in the universe. And you can imagine that where exactly the gas becomes hotter than the CMB, how fast that happens, etc., and how it happens as a function of position on the sky, has extremely interesting information on, say, the nature of the very first sources, right? Whether they were X-ray sources. If there's no X-ray sources, no accreting black holes in the early universe, then this gas temperature the heating will take place much later, for example, right? So there's a lot of information just in the temperature evolution of the IGM at very high redshifts. And we'll come back to this later. Right, so one way of going about doing this is with the 21 centimeter line, and then just indicated this 21 centimeter line in the context of this energy level, this energy diagram of the hydrogen atom that I showed earlier. Hydrogen atom of the 21 centimeter line corresponds to the hyperfine transition in the ground state of atomic hydrogen, right? So it's all the way here. 21 centimeters, the energy difference. Now, one thing that I think is funny about this particular state is what you often see is the following, right? So this 21 centimeter transition corresponds to the energy difference between these two states, right? So in one state you have a proton and an electron spinning in the same direction. In the other state, you have the proton and the electron spinning in opposite directions. And the idea is that, your proton is it's a spinning charge, basically, right? So you can imagine if you have a spinning charge, it acts like a magnet, right? So it has its own magnetic field lines, And because of that, the orientation of the electron itself, which also acts as its own little magnet, basically there's an energy difference in the orientation, depending on the orientation of the electron spin. Right? This is often what you see as the origin of this energy difference. But the funny thing is, if you look at quantum mechanics and you actually look at the calculation, that's just a calculation in the standard textbook, right? There's nothing special about this. The actual energy difference between these two states in quantum mechanics is zero, right? There is no 21 centimeter line in this particular. There is no energy difference between these two states. So where does it come from? Well, it comes from the moment, actually from the term when R is zero, so when the electron is inside the proton, right? which is pretty bizarre. So, it's kind of, to me, it's kind of remarkable to think about this, is that, this 21 centimeter transition is an extremely rare transition, right? If you have a hydrogen atom in the excited state of this transition, then it takes, I think, 10 million years for the atom to radiatively cascade down to the ground state, right? Spontaneously. And one way you might look at this is that, well, yeah, that's because, this it just doesn't happen very often that the electron is inside the proton, right? And I mentioned this in the first lecture that quantum mechanics allows there is a non-zero probability for this to happen. Right? Okay. In any case, irrespective of how you believe this line originates or how this line originates, and I already mentioned in earlier lectures that it has been a very successful and useful probe of galaxy dynamics, etc. It has given us rotation curves of nearby galaxies, which provided additional evidence for dark matter inside of galaxies, right? But detecting the 21 centimeter line from this very distant universe, or redshifts 6 up to 20, is one of the main science drivers behind many low frequency arrays that are currently being built, or including the Murchison-Wide Field Array in Australia, LOFAR here in Europe, right? In future, the Square Kilometre Array in South Africa and Australia. And there's others, such as HERA, or the Hydrogen Reionization Array, right? Or PAPER, the Precision Array for probing the epoch of reionization, right? So there's a whole bunch of these arrays that are really trying to to detect this particular line. Right, so I'm just going to briefly go over the physics and radiative transfer of this particular transition, right? So again, 21 centimeter transition corresponds to the energy difference between these two states of the ground state of atomic hydrogen. And the idea is that, if you have a gas cloud of hydrogen sitting at some very high redshift, let's say redshift 20 or something like that, that cosmic microwave background photons will have to propagate through this particular cloud, right? They pass through, and the hydrogen, most of the hydrogen which is in the ground state, can either absorb or can either suppress emission from this background, cosmic microwave background, or they can add to it, right? And that process is described by the radiative transfer equation, which is given here, right? And it's written in a slightly different form, but very similar to the one that we discussed when we were discussing the radiative transfer, right? So I wrote this one down, so you have the angle averaged intensity, that's basically the same here. I have this line profile function, which is not here, but that's just, that doesn't really matter. I think that's actually just a notation thing. In any case, so here, for example, I had a source function, which is volume emissivity over an opacity term, right? And that's, you sort of see that this term enters here as well. It's written in a slightly different form, but it's really the same equation. But what is important about this equation is that you can sort of see that the fate of what happens to the intensity of the CMB is set entirely by the number of density of atoms in the ground state and the excited state, right? N0 and N1. And that makes sense. Right? For example, well, one thing you can see, for example, when this term becomes less than 1, or when this term is less than 1, this term is negative, right? So you sort of absorb, this term is negative, so you absorb CMB photons as they're passing through the cloud. On the other hand, if this term is positive, right, and this term is positive, and the radiative transfer actually adds photons to the CMB at this particular location. Now, this quantity n0 over n1, or n0 over n1, is usually written in as slightly differently. It's written as the excitation temperature of this particular transition, or the spin temperature, right? So this ratio is just Ts, just rewritten slightly. Right, so then you can, if you look at this equation, then the radiative transfer is set entirely by the spin temperature of the gas. You know, whatever the gas does to the CMB, it's set entirely by the spin temperature. Now what you can do, we're going to rewrite this radiative transfer equation in a slightly different way. So this is the standard radiative transfer equation that I just had on the board. In radio astronomy, it's common not to work in units of intensity, but to work in units of brightness temperature. Right? And they're related just through a simple multiplication factor. Right? So intensity at some position x in the scale of the CMB at a frequency nu is just the temperature at that particular location. The brightness temperature is just that multiplied by some factor. Actually, that's lambda squared here. Sorry, factor of 2 missing. And this is just the common practice in radio astronomy, right? So if you rewrite the radiative transfer equation, you can look at how the temperature, which you just should see as an intensity, right? The temperature change in the CMB as the radiation is passing through this cloud is given, the temperature change is given by this expression here, right? And I'm not going to go through this derivation, but the temperature change is of the order of 27 millikelvin for gas at mean density. And there is this term in here which contains the spin temperature and the CMB temperature. So this is the equation that you usually see when you look at CMB, when you look at studies of 21 centimeter of the distant universe, right? It's usually written in terms of this brightness temperature brightness temperature change of the cosmic microwave background. And remember that the CMB has a temperature, of a few Kelvin, for example. So this is it's a very small fluctuation on top of that, of the CMB. So that's the fact that this fluctuation is small means that the gas is very subtly perturbing the background CMB, right? So very optically thin. Very different than Lyman-alpha. Now what this equation actually shows you is that, this signal that we're interested in, this brightness temperature induced by the neutral hydrogen in the universe, depends on the neutral fraction, obviously. Like the more neutral hydrogen gas we have, the stronger the signal is. It depends on the overall density and the spin temperature factor. The neutral fraction is of course great for reionization, and this is why all these low frequencies arrays are being built, right? HERA, the Hydrogen Reionization Array, Precision Array for Cosmic Reionization. I don't know exactly what it stood for, but it's entirely because of the dependence of the brightness temperature on the neutral fraction. Now the baryon density, of course, the sensitivity to baryon density gives you with a very, very nice probe of cosmology, right? Because you can basically probe the 3D distribution of baryons throughout the universe very early on, right, if you can detect this. And of course, the spin temperature. So, the reason I want to talk about this is that the spin temperature actually has some very interesting connection with Lyman-alpha scattering. And next, what I'll talk about is that the spin temperature turns out to be always somewhere between the CMB temperature and the gas temperature, right? And that has some very strange and interesting implications, right? So this is again the equation that I had up before. So the change in CMB temperature due to neutral hydrogen is the order of 30 millikelvin for a neutral universe at mean density, and this particular multiplied by this factor that depends on the spin temperature. But here's what the spin temperature actually looks like, right? So the spin temperature is some sort of weighted average of the CMB temperature, which is this blue term, and the gas temperature, which is this black term. Now there's this, and just to emphasize where this comes from, right, we know that remember that the spin temperature is entirely a statement of the population of atoms in these two states, right? So what this equation actually tells us is that there is a connection with the CMB temperature, and the reason for that is that the CMB, we know that the CMB radiation of the CMB can excite these transitions, right? This is what sort of makes this, in principle, makes the hydrogen visible in the first place. So the fact that the CMB can interact with this transition sort of suggests that there is a coupling between the CMB temperature and these and the relative population of these two levels. Similarly, if we have hydrogen atoms colliding, these collisions can induce changes in the level populations of these two species. This will drive the spin temperature to the gas temperature, right? And this is just collisions. Now the red term, which is what I'm interested in, or what I want to talk about today, and this is known as the Wouthuysen-Field Effect, right? And that's actually, a pretty cool effect. So what this actually says, there's two terms that we need to understand. So X alpha is a rate that depends on the scattering rate of Lyman-alpha photons in the universe. And this T alpha is something that is known as the color temperature of the Lyman-alpha radiation field. And I'll explain that, I think, next. Yeah. But let me first say that the scattering rate is something that is, when we do Lyman-alpha Monte Carlo radiative transfer, this is basically something that you can extract from Monte Carlo simulations trivially, right? We can get it as you're doing your calculations, we know exactly where which photons scattered. So we know exactly for each cell in the simulation what the scattering rate was, right? How many photons scattered there, etc. So what is then this color temperature? What does it do? So Lyman-alpha scattering, Lyman-alpha absorption and subsequent re-emission affects these level populations. Right? An atom can be in this state or this state. If you have your Lyman-alpha photon, if you get excited by a Lyman-alpha photon, you basically go to one of these 2p states. I haven't drawn fine structure and hyperfine structure splitting of the 2p state in this case. You go to one of these states, you come back down again. Right? That starts mixing the level populations here, right? Because the radiative cascade back down is sort of set by branching ratios that I talked about in lecture 2. Right? It's set by the transitions rate from whatever state you're in into this versus this state. Right? So there's mixing going on. Now you can imagine if you look at this, that it takes a slightly higher energy Lyman-alpha photon to excite the lower state than the higher state. So you can imagine if you have a population of Lyman-alpha photons, all of which were slightly more energetic than the Lyman-alpha resonance. These photons would likely be slightly more likely be absorbed by this particular state than this particular state. Right? So there's a preference to depopulate the ground state versus the excited state. So this statement sort of suggests that it's actually the spectrum of Lyman-alpha photons that has, So these animations are kind of distracting for myself, I mean, you're sort of in the flow of a story, and then suddenly it's like, oh, why did I do that? It seemed like a good idea when you're preparing the slides, and I was like, oh, let's put in a nice animation. In any case, so the spectrum of Lyman-alpha photons around the resonance is what really it can have a pretty big impact on these level populations, right? Well, big is a big word, but what you have to realize is that these are very subtle changes in the energy in the level populations that you need to get an interesting signal, right? So we're looking at all kinds of subtle effects that can have an impact, and this is definitely one of them. Oh no. In any case, so the color temperature is just represent a measure of the spectrum of the Lyman-alpha photons around line center. It's basically the slope of the Lyman-alpha spectrum around line center, as you can see here. It's just dj, d nu, so the slope, basically. Now, right, it might be a problem here. I mean, if you remember from the lecture where I was discussing frequency diffusion, right, I had this plot here. I was saying, like, as photons diffuse away from line center, right, they diffuse in frequency space. So I plotted, say, if you were to look at the frequency distribution of photons far away from the center of the sphere and plot the number density of photons as a function of frequency, I was saying that because of this diffusion, the spectrum gets really broad and sort of flat around the center here. Right? So if you look at the spectrum, if this is really what is happening, and it actually is very close to what is happening, if this is what is happening, the slope is 0, right? And if the slope is 0, then, well, this approximation is actually not that good, because it's 1 over 0 is infinity. Right? So something is not quite right. Now, this is actually what is amazing. This is when George Field came to the rescue in 1959. It turns out that this is not exactly flat, right? And it's not flat because of because of something that we already discussed in another lecture, in lecture 4, I think. Yeah, lecture 4. So if you look at the spectrum in very close detail, you zoom in, you actually see that it's not exactly flat across the Lyman-alpha resonance. It has a small slope. Right? And the reason for this is related to this effect, which we call recoil. Right? And I'm not sure if you remember this, but I was saying in the frame of the hydrogen atom, energy is conserved, was perfectly conserved, is what I first discussed. But then I said, well, it's not exactly the case, because in this case, for example, if you absorb a Lyman-alpha photon in the frame of the atom and you scatter it in this direction, then because of energy momentum conservation, we know that the atom must get a little kick in this direction. Right? So there's a little bit of momentum transfer from the photon to the hydrogen atom. And it turns out that this kick, actually, the kick that this recoil effect, turns out to be responsible for inducing a slight change in the frequency around the Lyman-alpha resonance. And this actually drives the color temperature to exactly the gas temperature. Right? And I think this is why, this is why we call this Wouthuysen-Field. Right? Wouthuysen indicated that the scattering of Lyman-alpha photons, or the spectrum of Lyman-alpha, is what is really determining this color temperature of Lyman-alpha, and Field's results showed that this color temperature equals the gas temperature. Right? So that sort of, like this complicated expression really says that the spin temperature is somewhere between the CMB and gas temperature. Where it is exactly, that depends on a number of things, but yeah, it can only be in between these two temperatures. Okay, so I'm just going to put up this slide again, which shows the evolution of gas temperature as a function of redshift for both the gas and the CMB. Right? And we know that the spin temperature is somewhere in between these two. Right? And the other thing we know is that from the radiative transfer equation, I don't know if I'm showing that here. No, I should have shown that here. The other thing we know from the radiative transfer equation is that it is, if the spin temperature, for example, is larger than the CMB temperature, this term is positive. Right? So that means that the brightness temperature, or the excess brightness temperature of the hydrogen, is positive. So you get basically additional emission. You see the hydrogen in 21 centimeter emission. On the other hand, if this term is negative, this brightness temperature is negative, so you get absorption with respect to the CMB. Right? So this is the key quantity that determines whether a hydrogen is going to be visible in emission or absorption. Right? Just wait for the bounce. Right, so you can already see here, for example, the CMB is going to be, the spin temperature is going to be between the gas and CMB temperature. Here, the hydrogen, we can already see it should be an absorption. Here, it's going to be an emission. You can already see that. Now, it's actually it's a bit more complicated than that, slightly more complicated, and even, I think, more interesting. Right, so that's because we know that this Wouthuysen-Field effect, right, which is this Lyman-alpha coupling, only kicks in if there's Lyman-alpha photons around. Right? And as we understand it, the only Lyman-alpha photons that can be around would be produced by stars. Right? So this effect kicks in once the first stars form. This is when we have the first injection of UV photons into the IGM. And just to emphasize that these are not Lyman-alpha photons necessarily that are, we see as Lyman-alpha coming out of galaxies. This is basically any UV radiation in between the Lyman-alpha and ionizing photon threshold. Right? Because these photons, say you have a 13.5 eV photon, that photon will freely escape into the neutral IGM. It will probably hit one of the Lyman series resonances first, And then you have one of these radiative cascades that goes down and you get a Lyman-alpha photon. Once you have a Lyman-alpha photons, you have incredibly frequent scattering before the photon escapes. Right? So it really starts, So the Wouthuysen-Field effect is linked to the formation of the first stars and galaxies. So in a sense, just to emphasize that, we talk about radiative feedback in the early universe, but this Wouthuysen-Field coupling effect is actually you can see it as one of the first radiative feedback effects in the universe, right? Or the first effect. And it has a noticeable impact. So this is from the DARE, the Dark Ages Radio Explorer website. It's just a nice cartoon of this global 21 centimeter signal that I was showing you earlier, right? And then earlier on I was sort of saying, like, we know that the hydrogen is going to be an absorption at very high redshift, and it's going to be an emission at lower redshift, right? That's exactly what this plot shows, with some extra wiggles, and I'll explain these in a second. But redshift is going, high redshift is now on the left side, low redshift is on the right side. And my plot earlier on, I was saying, like, low redshift, the gas temperature is above the CMB temperature, spin temperature is going to be somewhere in between, so we're going to see hydrogen in emission. That's exactly the case. Hydrogen is in emission here. At some point it disappears because the universe gets reionized in this cartoon. Right? At low redshift, the gas temperature is below the CMB temperature. We expect the CMB temperature to be somewhere here. We should see the spin temperature to be somewhere here. We should see it in absorption, and that's what we see here, right? The brightness temperature is negative. And millikelvin, right? So my number was indicating minus 27 millikelvin. That was, I think, at redshift 10. That's the order of magnitude of the signal we're looking at here, right? So that all seems fine. Now, as you can see here, what is interesting is that this signal is negative. Here they indicate stellar ignition, so the first stars form at a redshift of 30 in this cartoon. Now, when that happens, the Wouthuysen-Field effect kicks in, and that drives the spin temperature to the gas temperature. Now, that's the interesting thing is that we think that this Wouthuysen-Field effect really is the very first radiative feedback effect. So it actually starts coupling the gas temperature to the spin temperature to the gas temperature before significant heating took place, right? So it actually drives the spin temperature, we think, really to the gas temperature at its lowest value, well, as basically to very low values, right? So a maximum temperature difference between the CMB and the gas spin temperature. Right, so this gives us pretty deep absorption, right? And it is then thought that at some point heating kicks in, right? When the first stars exploded, formed black holes, etc. The black hole started accreting, emitting X-rays. These X-rays started heating and driving the gas temperature back up until you cross the CMB temperature, at which point you see nothing, right? There's no signal. And then you see the hydrogen in emission. Right? But the cool thing is that the minimum here, this minimum in the brightness temperature, and this is what these global 21 centimeter experiments are going after now. It's thought to be it's really thought to be one of the, basically telltale signatures of the formation of the first stars and black holes in the universe, right? This is what they will go after. But the depth of this signal is very closely, very closely connected to the Lyman-alpha emitted by these very first galaxies and how these photons propagate through the universe, right? And the one thing I want to talk about today, and what I will talk about a little bit, not much, is that I think there's still a lot of open questions there that are quite relevant for these kind of predictions. Okay. It's remarkable. I mean, I'm not sure if I mentioned this, but I'm not sure if you can see it. It's probably difficult to see, but this is the moon. Right? This Dark Ages Radio Explorer would be on the far side of the moon, basically, because then terrestrial radio interference would be minimized. Right? I think right next to the fault, actually. Well, maybe not. In any case. So the interesting thing is, so this whole, the depth of this absorption feature, I guess it can be, it doesn't need to be dark anymore. I'm not going to show the moon. Well, I might as well show it now here. There's the moon here. Right, but in any case, Lyman-alpha scattering is crucial for setting this signal, right? Now one thing that, what sets this Lyman-alpha scattering rate are, of course, the first stars and galaxies, right? And we know that as these first stars turn on, etc., these Lyman-alpha photons start diffusing away through the neutral IgM, away from these first stars and galaxies, and until they stream freely, right? Now, if the universe were optically thin to Lyman-alpha radiation, the scattering rate would just fall off as r to the minus 2, which is this black line here. And the normalization here is not relevant, just discussing the effect. So you can imagine if the flux falls off as r to the minus 2 in an optically thin medium, the scattering rate goes as r to the minus 2. This is not the case, because we know that these Lyman-alpha photons are scattering, they're diffusing outward. So especially close to the galaxy, they're scattering more and more and more, but then they slowly diffuse away from line resonance, right? So their mean free path goes up, and they sort of take bigger steps until they stream freely, right? So you sort of get this pileup of Lyman-alpha photons closer to the galaxy, and eventually this pileup gets reduced and reduced until the photons are really free streaming, right? So it is a trapping effect. I mean, the photons, again, are not trapped for long. It's not giving rise to a delayed escape of Lyman-alpha photons, but it is giving rise to an enhanced energy density of the photons and an enhanced scattering rate. Right. So this is from a paper by Xu and Zheng, 2007. But the interesting thing is that you can actually start wondering about radiative transfer effects on interstellar scales, right? And for example, we know that these first galaxies are actually, would likely have very large column densities of H1 and even H2, right? And both H1 and H2 can absorb UV photons on the interstellar level. And it's interesting that if you put in, a column density that is quite reasonable for first galaxy, and you plug that in, you actually absorb out a lot of your photons that would be doing this kind of scattering. Right, and this is a master's student in Oslo who did these calculations a while ago, but what he showed is that if you account for this interstellar absorption of these UV photons, or just a simplified model of it, it's amazing what the effects are for the overall scattering rate of Lyman-alpha, the overall Lyman-alpha scattering rate away from the galaxy. It can actually go down by orders of magnitude. Right, so I think, what this actually might mean, this is something that we're still working on. But again, I think it is yet another application of how interstellar radiative transfer can actually affect cosmological radiative transfer in a big way, right? So I think it's really important to do this, to understand this. So this gives us an opportunity, right? And this is what I was asking Matthew about. This gives us an opportunity to link some of the future telescopes that are going to really revolutionize astrophysics in the future, and past telescopes that have revolutionized astrophysics in the past, right? The famous FOT here. So I was inspired by Matthew's diagram connecting all these different processes. And so I was actually sitting down and thinking very hard about how to have a connection between FOT, DARE, and the SKA, right? But the connection was actually, I think I suggested this. So Lyman-alpha is what is connecting these telescopes, right? It's actually quite difficult. I mean, it took me a long time to figure this out. And now that I see it, I start to doubt it actually myself, but we can discuss afterwards. In any case, in any case, how much time do I have left?
5 minutes more or less.
Okay, but then 5 minutes is enough to summarize what I said. So these are the things what we talked about, and I was discussing with Anne. So all this stuff that I talked about is in these lecture notes, right? So these lecture notes, I'll have to update a little bit, right? But these lecture notes, what I'm going to do is, what was I going to do? Oh, right, yeah, in a few weeks' time, I think they're ready, right? So if you're interested in getting a copy, you can either email me or Ann, right? And I can send you an early draft, which is, I think, ready. But I'm pretty sure it's going to be full with typos and stuff like that. So, if you want a copy, let me or Ann know. You'll get one. And if you find any typos, mistakes, or if anything is unclear, let me know, and I'll try to fix it. And I'll try to post it on May 31st. Because, I think we were supposed to post it on June 1st, right? So I'm actually going to be very good and do it one day early. In any case, so I guess what I want to end with thanking you for coming. I mean, I think I've been very impressed with the attendance. As you know, when I was a student, I wasn't there all the time at all. I'm also very impressed that you were very actively participating, like in these discussion sessions. I like the questions. It's been really fun talking to you, and I wish you good luck in this field or whatever field you work on. And finally, a nice thank you to the organizers for, it was really great. Thank you. So what is happening? So the question was, why is there another dip here and another peak here? So the answer is that initially, so the spin temperature is always between these two temperatures, right? At very high densities, initially the spin temperature follows the gas temperature because it's the collisions that couple the spin temperature to the gas temperature, right? So you sort of see this increase in the difference between the spin and the CMB temperature, which gives rise to stronger absorption. And at some point, at a particular redshift, the collisions simply become not efficient enough. And at that point, it's actually the spin temperature goes back to the CMB temperature. Right? So then the spin temperature sort of crawls back to the CMB temperature and the signal starts disappearing. Right? And then at some point when the first stars form, and they insert the Lyman-Werner or the UV photons, then actually the Wouthuysen-Field coupling brings the temperature back again to the gas temperature. Now, of course, whether this peak occurs here, or it depends on a number of assumptions, right? It depends on how efficient you produce UV photons, how efficient you produce X-ray photons, etc. So all of these parameters affect the precise shape. Right, but that's the goal of this experiment, is to sort of determine the shape and put constraints on these parameters, basically. It would be our first constraint on this very high redshift universe. Yeah, I think you, yeah.
You mentioned that you might, that you have these two hyperfine.
Right.
Going on? I mean, if so, how significant could it be?
So People have looked at this, whether 21 centimeter can maze or laze, right? And I've actually looked at it as well, but it's very difficult, right? And one way, like the Lyman-alpha actually gives you a natural pump, right? It's kind of ideal. It's the ultimate, yeah, it's the perfect pump for this. I mean,
That's exactly the but
so but it would.
you need to maintain a population before.
Well, so the idea is that, you know, if your color temperature would have, if your color temperature would somehow be different than the gas temperature, then it could happen, right? But in practice, it is very difficult to have the color temperature be different than the gas temperature. We wish, you know, if it were possible, I think it would have been awesome. But, you know, if you,
It would be fantastic if it just kicked in and then stimulated.
yeah, exactly. The collisions, I think people have looked at this as well, and the problem is that collisions, you know, if you want to increase the efficiency of collisions, then, you know, the collisions tend to drive the excitation temperature to the gas temperature. So then there's, you know, it's nice, but it will just give you either absorption or emission depending on the gas temperature. So I think the collisions are not really efficient at doing this. But the Lyman-alpha pumping might, but it doesn't seem to be working at all, actually. Yeah. But I like that question. I mean, I wondered about this as well. Yeah.
Is the Wouthuysen-Field effect important for the measurement of 21 centimeter in regular galaxies?
Yeah, that's a good one. I don't think so. I mean, and part of the reason I'm saying that is that the scattering rates, you know, so it's a bit related to, you know, the ISM of ordinary galaxies is less, I guess, less susceptible to the frequent scattering of Lyman-alpha photons to really. I guess because of the velocity gradients, the multiphase nature of the ISM, etc., Lyman-alpha photons scatter much less than in, say, the neutral high redshift IgM, right? The neutral high redshift IgM, we know they're going to scatter 1 million times. We don't know that these photons are going to scatter. You know, if you have a wind in a galaxy, the Lyman-alpha photons might just scatter boom, boom, right? They might scatter twice and be out of the galaxy. So, I mean, it could be interesting. I think, for example, 1 Zwicky 18, right? If it's true that there's a large column of dust-free gas stationary, right? That would be there. It could be interesting. But to be honest, I haven't looked at it in much detail. I mean, it'd be interesting to check for like strange departures of the spin temperature with respect to the gas temperature.